In probability theory, we use a certain type of functions called probability density functions to encode different ways of picking a number at random. But how does this work? More specifically, if you were given such a function, how could you use it to sample a random number? Here is a preview of the end of this video, where we use some physical device to sample a random number. Hopefully, what is happening in this clip should make sense by then. For now, let us explain the theory behind it. First, let us describe the type of functions that we consider here. Starting with the function f that takes any real number x as an input and that outputs a real number f of x. We say that f is a probability density function, or PDF for short, if it satisfies the two following conditions. Condition 1, every output f of x of the function is non-negative, which corresponds to the graph of the function lying above the x-axis. Condition 2, the total area of the region that lies between the x-axis and the graph of the function should be equal to 1. In mathematical terms, we write this condition as integral from minus infinity to infinity of f of x dx equals 1. Maybe it's time for a quick reminder about integrals. If you start with a function f with non-negative values and two numbers a and b with a smaller than or equal to b, the mathematical expression integral from a to b of f of x dx denotes the area under the curve of f between a and b, that is, the area of the region colored in red here. In the second condition above, a is minus infinity and b is plus infinity. So the region that we consider extends infinitely to the left and to the right. Now, let us consider some arbitrary PDF and call this function f. As we represent the graph of f, imagine that the region under the curve is made of billions and billions of microscopically small grains of sand. These grains of sand would be evenly spread out under the curve so that the number of grains of sand inside any portion of that region is proportional to its area. From there, we can define the following random experiment. Among all the grains of sand under the curve, pick one uniformly at random. Let us say that I happen to pick this one. Then, we measure its x-coordinate and call capital X the obtained value. So x is a value that is determined by the result of a random experiment. In probability theory, we say that x is a random variable, which is a fancy way of saying random number. In the end, we started with some PDF, and we presented a recipe to get a random variable out of it. Now, what can we say about the distribution of this random variable? Meaning, how can we describe what values it can take with what probability? First, notice that if on some interval the function outputs 0, then there is no sand in the pile above it, so the probability that x is in that interval is 0. In fact, for any two numbers a and b with a smaller than or equal to b, let us compute the probability that x is between a and b. In order for x to be between a and b, we need the random grain of sand to be picked within the red region. Because the grain of sand is chosen at random, this happens with a probability that we can express as the ratio of the number of grains of sand in the red region divided by the total number of grains of sand. Because we said that the number of grains of sand in any region is proportional to its area, this ratio is just the area of the red region divided by the total area under the curve. Since we assume that f was a PDF, the denominator is just 1. This means that we have a very simple way of expressing the probability that x is between a and b. It is just the area of the red region, which we can express as the integral from a to b of the function f. This last property characterizes the distribution of x. We generally summarize it by saying that x has probability density function given by f. In practice, random variables with PDFs are used all the time in probability theory. Let us take a closer look at two distributions that each belong to a larger family of distributions that you may have encountered in class. The standard Gaussian, which corresponds to a function f of x equals 1 over square root 2 pi times exponential minus x squared over 2 whose curve has this bell shape, and the uniform distribution on the interval 0, 1, which corresponds to the function f of x equals 1 if x is between 0 and 1, and 0 otherwise. For each of those two, if you want to understand the associated random variable, you can use the mental picture that is presented in this video. See the region under the curve as a pile of sand, pick a grain of sand at random, and measure its x-coordinate. The locations on the line where the pile is higher have more sand above them, so that is where the random grain of sand is more likely to be picked. In the case of the standard Gaussian, the pile is highest at 0 and decreases when you get further away, so you can get the idea that the values close to 0 will be more likely than the larger ones. On the contrary, in the case of the uniform distribution, you can see that on the interval 0, 1, the pile of sand is perfectly even, so no specific value between 0 and 1 is favored. Okay, so now let me show you device that I designed to illustrate the idea that I explained in this video. Here, I have chosen a specific density function f, where f of x is 3/2 minus x whenever x is between 0 and 1, and f of x equals 0 otherwise. I'll let you check that this is indeed a PDF. Okay, so this is the outline of my pile of sand. And here in this jar is my sand. So you can see that it's made of a few certain number of identical white beads together with one single blue bead that is completely identical to all the other beads. So now if I shake this jar, if I shake it for long enough, then all the beads are going to be completely mixed. And now, because all the beads are identical, they all play symmetrical roles, so that the blue bead in particular is going to play the role of a random bead. So now what I just have to do is pour this sand in the outline of my pile and measure the x-coordinate of the blue bead. So let's do that. So this is what we're going to do. I'm going to pour all the beads under the curve of my function. Then we just have to spot the location of the colored bead, maybe here, for example, and measure its x-coordinate. In my example here, the realization of my random variable x, my random number, is about 0.16. Okay, so let's do it for real this time. I have my jar here where my beads are completely mixed. I'll just pour them under the graph of the function. And voila! Here in blue is our random grain of sand, so we can just measure its x-coordinate to get our random number. This time it seems to be very close to 0.5. Okay, well, I hope this demonstration gave you a bit of intuition about random variables with PDFs. In the future, I would hope to construct similar devices, but for more involved or more interesting probability density functions f. So yeah, I hope to do that in the future. For now, well, thanks for watching.